Okay, here we go. So you read about the rocket-powered basketball. You read about the rocket-powered basketball. So I have some questions for you so we get oriented correctly here, okay? So this function over here on the right is v. Is it a rate of change or an accumulation function? What are its dependent and independent variables? Talk for 30 seconds. Go. What kind of function is v? That's all I need to do. Okay, rate of change or accumulation? Rate of change. What's its dependent variable then? What's the dependent variable of this function? Velocity. Rate of change of height of the rocket. Rate of change of height. Okay, what's the independent variable? Time since. You got, whenever you define a time variable or a distance variable, you have to have that reference, that starting point, that since when or from when. So time is just not going to cut it. Time since launch. Time elapsed since launch. Okay, so v is a rate of change function. Relates the velocity of the rocket to the time elapsed since launch. Okay, we want to develop an accumulation function associated with v. What are its independent and dependent variables? 30 seconds. Go. Okay, independent variable for the accumulation function. Time elapsed since launch. You should have said time elapsed since launch. Dependent variable for the accumulation function. Height of the rocket above the ground, or from the launch pad. Okay? Accumulation h is the height of the rocket as a function of time elapsed since launch. Okay, we're getting just laying down all the groundwork here. Next three questions. Express the coordinates of the point on the given graph when t equals 5. That's the freeze that I'm showing here. I'm pausing the animation. I'm showing for t equals 5. What does the value v of 5 represent? And what does that mean for values of the accumulation function? Go, 2 minutes. 2 minutes. This is the most important question, maybe of the whole last month. Should be able to articulate what's happening here. What does v of 5 have to do with the accumulation function? Okay, what are the coordinates of that point at t equals 5 on that graph? Yes, Joseph? He wants 5 v of 5. What do you think? That's right. That's it. That's what you should have said. 5 and v of 5. Okay? What does the value v of 5 represent? Does the value, how about somebody new? Yes, sir? The acceleration. V of 5 is the acceleration. Agree? No, how about right here? The rate of change at the moment 5 seconds. Rate of change of what? Rate of change of time? Rate of change of distance? Getting closer? What did we say the dependent variable of the accumulation was? Height, right? So, yes, it's the rate of change at the moment t equals 5, the rate of change of height. The rate of change of the rocket's height at the moment t equals 5 seconds. Okay, here's the most important question. Have we learned something this semester? What does that value, v of 5, mean for values associated with the accumulation function? Somebody new? Joseph, you can go for it. Go for it.
Is the instantaneous velocity of 5 seconds?
That's not answering my question. What does it mean for values associated with the accumulation function? What's our independent quantity in this accumulation function? Time elapsed since launch. What's the dependent quantity? Height of the rocket. So I'm talking about those quantities. What does v of 5 have to do with those quantities? In the back. Oh, you started off great. You said that the change in height will be equal to? That was right. That's the right start. Yeah, right here.
The moment of height is the distance traveled of the height will be equal to the rate of change at 5.
The distance does not equal the rate of change. Right there.
dy equals v of 5 dx.
But what's y and x? We don't have y and x.
Change in y, or the change in height is equal to v of 5 times the change in time.
You got it. You got it. Okay? A change in height of the rocket is v of 5 times the corresponding change in time, or dh equals v of 5 dt. dh equals m dt, and m is our momentary rate of change at t equals 5. Okay. How many people got it before we went over it? Not enough. How many people are going to get it the next time? Okay, huge, important. That's what a rate of change is. A rate of change tells you that the change in your dependent quantity is that rate times whatever change in your independent quantity. It should at least feel familiar. Does it feel kind of familiar? We've been doing it a lot. We've been going over this a lot. Okay. So let's find the approximate height of the rocket. So our goal is to build. So here's a picture. What is this picture showing now? This picture is showing. We're gonna break up time into moments of 0.9 seconds. Is that a big moment or a small moment? 0.9 seconds. Very big. Right, we think of a moment as a small change around a value. So a moment of 0.9 seconds is a very large moment, but it's helpful to blow things up for our understanding, right? Okay, so these are very big moments, 0.9 seconds. Because look how much the rate of change changes over 0.9 seconds. It changes a lot. And when we think about the rate of change in a moment, we're thinking about that it's essentially constant for that moment. Well, that's for 0.9, that's not true at all, right? For 0.9 seconds, our rate of change is anything but constant. It's changing a lot. But for purposes of understanding, we want big moments help us to actually do something and understand what's going on. Okay, so we're going to use moments of 0.9 seconds, and then this is what we're going to use to the symbol delta for. So far we've talked a lot about dt, a little change in time. So delta t is going to be our notation to mean a whole moment. So it's more like a parameter than it is a variable. Okay, it's a fixed. We're going to take the situation. We're going to fix delta t at 0.9. That's going to be our width of a moment. Okay, and then we're going to take the rate of change at the beginning of each moment, and that's what this picture is showing. So in the first moment of 0.9 seconds, we're going to take the rate of change at the beginning, which is, that rate is 0, right? And so we'll have a rate of change of 0 for that whole first moment, that first delta t interval. And then the next delta t interval, or that whole moment, we'll use the rate of change at the beginning of the moment. So how would you express that rate of change exactly? So how would you express that rate of change in our second moment exactly? Talk to your neighbor. So, the constant rate that we're using for the second delta t interval, how would we express it exactly? Yes, sir. Nope. We're going to express this rate of change in that second interval. What would it be? Yes, sir, ma'am. V of 0.9. Agree? That's what it is. V of 0.9. Why? Because it's the rate of change at the beginning of this moment. The beginning of this moment is t equals 0.9. And so that whole constant rate in the second interval is going to be v of 0.9. That should make sense. Does that make sense? Okay, and then what will, in our third delta t interval, or third moment, how would we exactly express the rate of change that we're going to use as that momentary rate of change, constant rate of change? What would it be? V of 1.8, the time at the beginning of that moment. That's V of 1.8. Okay. So we want to use the principles we've learned so far now to approximate the height of the rocket at t equals 5 seconds. So that's what I'm showing right here. I'm showing t equals 5. And we want to approximate the height of the rocket at that time. Well, that means we have to consider two different things. We have to consider all changes in height accumulated within all the completed delta t intervals before t equals 5, and then there's a little more change in height in the current delta t interval. Okay? So these are what we call the completed delta t intervals. How many are there for t equals 5? How many are there for t equals 5? 1, 2, 3, just count. 5 of them, right? So there are 5 completed delta t intervals. But then that only goes up to time equals what? So we got 0.9, 1.8, 2.7, 3.6, and 4.5. So there's another half second. And this is now the current interval. So right now, t equals 5 is in the interval from 4.5 seconds to 5.4 seconds, and we call that the current interval. Because even though I've paused the animation, we have to think about t increasing continuously, right? T is going to start at 0. It's going to increase continuously. And as it does that, it's going to leave behind completed intervals. And then anytime we pause, there'll be some current interval. So now we've paused at t equals 5, and we're in the current interval that would be between 4.5 and 5.4 seconds. That's called the current interval. So if we want the total accumulated height at 5 seconds, we got to add up all the height from the completed delta t intervals and then the little amount in so far in the current delta t interval. Does it make sense? Okay, so let's do that. So in the first interval, how are we going to get the change in height due to that first interval? How do we calculate the change in height due to the first interval?
The final height minus the initial.
No, not final height minus initial height. Somebody in green shirt back there. Yeah. Okay, so first interval, m dt. So what is m in the first interval? How do we express it? V of 0, m times the total change in time, which is 0.9, or what we're calling delta t. So that's going to be 0 times 0.9. So that's for that completed first interval. The change in height is going to be m times the change in time, and our m comes from the velocity at the left side, v of 0 times delta t. Okay? And then we go on to the second interval, and we're going to add on a little bit height from the second completed interval, which will be m delta t. What is m? V of 0.9 times it's complete. So all the completed intervals have the same change in time, delta t. So v of 0.9, so I didn't write down the function. Was it t to the 1.3? What was it? T to the 1.3. So that this is actually defined as v of t is t to the 1.3 power. So what is v of 0.9? T to the, 0.9 to the 1.3 times delta t. So that's the total change in height from the first two completed intervals. Okay, you finish it. Go, finish it. Finish out the 5 completed intervals. We want the total change in height from the 5 completed time intervals, delta t intervals. Anybody, before we do that, anybody have a question? I see some eyes like, what the heck? So please ask. Oh, so the function is defined as, the velocity function is defined as t to the 1.3. The velocity function is defined as t to the 1.3, which we hadn't said up till now. Okay?
Obviously, like I didn't do the questions, it was just mark there.
Yeah, if you want to, we can see if we get it working after class, and you can answer it after class.
Why, but I mean, I don't know why, it's just not working.
Yeah, so, okay, well, let's try after class, and if not, then we'll do it at a different time when you can get it working. completed, yeah. Okay, so we're using the mathematics of constant rate of change. MDT plus MDT plus MDT. Getting all these, accumulating these little amounts of changes in height according to these constant rates that we're assuming for each moment. We're assuming a constant rate for each moment, which results in an approximate result, right? Because clearly it's not, clearly as soon as you start going into the interval, as soon as you move into this interval, the rate of change is much different, right? So that's the effect of long moments, wide moments, okay? So anyone get a value? Do all this and get a value. 10.7, we'll round to 7.5. What are the units on that? Meters per second? Meters, accumulated height. Is this right? This is showing something closer to 10.5 in the picture. Oh, there's a good reason. Yeah, but that's going to make it even more. Yeah, we haven't done the current, but this is already more than what it looks like in the picture. Anyway, so we still have the current interval to do. So the current delta t interval, what rate will we use?
The picture is around 15 or 16. This time is like right around.
Okay, right. Okay, so what is the rate in the current interval? How do we express the rate in the current interval? V of 4.5. Okay, so the current interval is 4.5, and we're going to multiply that by 0.9, right? No. We multiply it by? The interval starts at 4.5 seconds, and our current value of t is 5. Therefore, what is 0.5? What do we use for the notation for this value of 0.5 right here? Does anybody know? It's how much change we have in the current interval. What is that? I heard someone say it. dt. This is dt. dt is how much change you have in the current interval, right? Because we said that these little changes dt, they change within the moment, right? Within the moment. So the moment is that 0.9 seconds, and then dt will vary from 0 to 0.9. And when we get to the next moment, what will dt start at? When we get to the next moment, at 5.4 seconds, what will dt start at? 0, and it will vary from 0 to 0.9. When we get to the next moment, 6.3, dt will start at 0, and it will vary to 0.9. So our current interval is where we find dt. And right now, so it's going to be, this is going to be v of 4.5 times dt. V of 4.5 dt. And our dt right now is 0.5 seconds. So we got 4.5 to the 1.3 times 0.5. And what does that equal? 4 or 5 or something? What is that? Do that quick. 4.5 to the 1.3 times 0.5. 3.53 meters. So, the total, our height, approximate height at 5 seconds is the sum of all the completed delta t intervals. Ooh, ooh, ooh. That's my warning. Hurry. That's my toe. Okay. Okay. All right, so the total then accumulated height at 5 seconds is the sum of all the completed intervals plus the partial amount in the current interval. So what is it going to be? 10.75 plus? And that is better, so that total amount is going to be, so our height at 5, our approximate height at 5 is going to be 14.28. Okay, that looks, and that looking from the picture here, so that looks right, a little shy of 15. Right, because this is our accumulation graph of height, and so our dependent variable is height in meters. And that's what we're calculating at 5 meters.
We haven't added the
I'm sorry?
shouldn't we have added 4.5 to the 1/3 power times 0.9 to that huge thing of 1? Is that
No, 0.5. In the current interval, we don't have a full interval.
It's not there. It's like not one. Consider all changes in height of the accumulator within completed delta t intervals. We only added four moments, not 5.
Oh, maybe you added 4, we added 5. Here's 1, 2, 3, 4, 5. And lots of people told me that was 10.75. I've listed out all 5 of them here. And we got 10.75 for those 5. So you know what you're doing. But you know exactly what you're doing. I can hear it from your question. So you're good. Just you got some kind of mistake somewhere. Okay. So now the real thing we want is we want to develop the function, not just at one moment at a time what height you have, but okay. Can I have everyone's attention? Okay, can you whisper? Okay, whisper. Okay, so we want a function that tells us the height at any time. So that's what we're going to do next. So we're going to build up this function right now. Okay, so let's do that. Because we don't want to have to do that every time we get a new time. We don't want to do all that work. All that work is really important for understanding what's going on. But now if I change it to 5.7 seconds, we'd have to do all that again. So can we come up with a function that will represent every height at every time? Okay. So in order to do that, we have to remember this very important kind of technique that we have up here. So here I'm showing, this is any moment right here, okay? And we're going to have a starting time of that moment, t sub s, and then all the accumulated height up to that t of s, okay? And then here now we're in, this is the current delta t interval, and we need to find, if we want to write the function, we have to know how to write what h of t is. Right? That's what writing the function would mean. Would mean for any dt in the current interval, what is h of t? So, can you do it? Can you do it in a minute? So using all the symbols there, can you write what h of t equals given that setup right there? Again, something we've been working on hard for the last 2 weeks. Can you do it? Last time I asked you, you all 100% of you told me you'd do it the next time. Let's see if we can do it. Go. Okay, I'll give you a hint. The broad structure is a sum. The broad structure of it is a sum of two things. How many got that? Oh, good. More. Okay. It's a sum of what and what? What's the first thing? Just in general, what is it? Whoa, all kinds of craziness. We're trying to find a height, so it's going to be the sum of two. So what is the... dH plus dt. Is it dH plus dt? What's the first thing we start with? The starting height. The starting height. Or all the accumulated height up to this moment, right here, this exact time, t sub s. Plus what? Just broadly, the most broadly thing. What's the starting height plus change in height, dH. And how do we write dH? So it's going to be, dH is going to be constant rate of change. We write dH as V of TS times dt. How many people got it before we started? It's the same thing we did before, but we got to know function notation. We got to know and be able to use function notation on all these symbols. The starting height plus the change in height, which is found by constant rate of change. The constant rate of change for our current interval times the little change in t. That's what that dH is. Okay, so here we go. So we're going to do this over and over again. So in the first interval, when t is between 0 and 0.9, dt is going to vary from 0 to 0.9, and we're going to use this, right? We're going to use this. It's going to be, well, our initial height is 0, okay? So we can just say 0 plus, what's dH? Well, it's going to be V of 0 dt. We're using this construct right here. All right, then the next interval. When 0.9 I'm not sure which side he puts the equals to. Is he putting the equals on the right or the left? Do you remember? Is he putting the less than or equal to on the right or the left side of the interval? Do you remember? I don't remember. Okay. What does dt vary in this second interval? It varies from 0 to 0.9. Okay? So what's the starting, okay? What's our starting height? Well, our starting height would be when t is 0.9. So if we were to plug 0.9 into this, it'd be our starting height, which would be V of 0.9 delta t. That's our total accumulated height up to that point, plus the change. So it'd be, V of 0. V of 0. Plus, so that's all the height accumulated up till that point. This is just to be plus V of 0.9 times dt. I don't have room. It's my favorite thing. No, not leaving. Oh, boy. No, that's my favorite thing. Okay. Okay, this is an interval from 0.9 to 1.8. Okay, so this is our total accumulated height in the first completed interval, plus, now this is the current interval, so we're going to have V of 0.9 times whatever dt is, as dt varies from 0 to 0.9. Okay, so we'll do one more. So the next one would be everything from the first interval plus everything in the second interval plus the current amount in the third interval. 1.8 times dt. And that would be from 1.8 to 2.7 as dt varies from 0 to 0.9. So we have to write this function one piece at a time. So we just wrote this piece right here. We got all the height up to 1.8 seconds, which was the sum of those first two completed intervals, plus then however much we've gone into the current interval, dt, times its rate. And so that will be true for t between 1.8 and 2.7 as dt varies from 0 to 0.9. We'd have to keep going to get all of it. We'd have to keep adding lines. One line in the function for each of these little segments. Okay. Sorry to keep you late. Have a good weekend.